This resource looks at examples with both the product and quotient rules being used simultaneously. Previous videos then have given a definition and a concise derivation of differentiation from first principles, and now we're looking at worked examples for slightly more challenging cases. Here the focus is on combining the product and the quotient rules while utilising a table of results for simple functions. So a reminder then, the product rule: if y is a product of two functions u and v, the derivative of y with respect to x is u dv dx plus v du dx. If y is a quotient of two functions, so y is u over v, then dy dx is v du dx minus u dv dx over v squared. Now, as in earlier videos, we're reminding you that it's assumed you have access to a table of common results, so you can just take the derivatives of these functions without doing them from first principles. What's the technique we're going to use then? First of all, define all the functions used in the product rule where it's used, and in the quotient rule where it's used, along with their associated derivatives. Ensure the layout of your work is uncluttered and unambiguous, and this will stop you making unnecessary typos. And obviously, use results from a table wherever possible to simplify your life. First example then. Find the derivative of f of x equals x squared log 2x cubed over x to the 5 plus 4x plus 1. So here you'll notice that u at the top here is a product of two functions, a product of x squared and log 2x cubed. So before I use the quotient rule, first of all I'm going to need the product rule on this numerator term. So the numerator, you can see it's given here as x squared times log 2 plus 3 log x, and I can write that as a product of p of x and t of x, and I've written down here what's the product rule. So du dx is p dt dx plus t dp dx. Now I've got the definitions for p. You can see p is x squared, t is log 2 plus 3 log x, dp dx is 2x, and dt dx is 3 over x. So all I'm going to do is take these values here and plug them in to this formula. So wherever they go, I'm going to take all the values and just plug them in. So you'll notice step number 1 was to say that my numerator is a product of two functions, and I need the derivative of the numerator. I need to know what is du dx. And I've solved it here in these two pink boxes. So there it is. Du dx is 2x times log 2 plus 3 log x plus x squared times 3 over x. Right then, let's go back and look at the original problem. So we've got u over v, and now we're going to use the quotient formula, which is dy dx equals v du dx minus u dv dx over v squared. Now on the previous page we derived du dx, and obviously u is the numerator. V is x to the 5 plus 4x plus 1, so dv dx is 5x to the 4 plus 4, and now I can plug these four values into this formula here. So I'm going to get that dy dx equals, so we start with v, which is x to the 5 plus 4x plus 1, times du dx, and I know this is quite a long term, so we're going to run out of space, but we get 2x into log 2 plus 3 log x plus 3x. So that's v du dx, and then we're going to get minus u. So u is x squared log 2x cubed times dv dx, which is 5x to the 4 plus 4. We just about fit it in, and then all over v squared, which is x to the 5 plus 4x plus 1 squared. Now I accept that this is quite messy, but the most important message for you to see is if you keep things neat and tidy, you make clear definitions of what you're doing, then all it comes is plugging the numbers into a formula. Right, next example. So h or g of w, is 4e to the 2w over w squared sec 3w. Now in this case, you'll see the denominator is a product of two terms. So I'm going to need the product rule in order to work out the derivative of the denominator. So here we go. The denominator is w squared sec 3w, and I'm going to write that as a function p times a function t. And then I can use the product rule, so dv dw equals p dt dw plus t dp dw. So p is w squared, there it is, and therefore dp dw is going to be 2w. T is sec 3w, so dt dw is 3 sine 3w over cos squared 3w. So all I'm going to do now is plug these values into this formula in order to find dv dw. So all I've done so far is use the product rule on the denominator because I want to find dv dw. That's all I've done on this page, find dv dw. Okay, so let's recapture what we've done. So we've said from the previous page we've computed dv dw. There it is. We also happen to know that u, there it is at the top, is 4e to the 2w, so du dw is 8e to the 2w. And so all I need to do now is plug all these values into my quotient formula. So I'm going to get dh dw equals v, which is w squared sec 3w, times du dw, which is 8e to the 2w, and then we get minus, and then u, which is 4e to the 2w, times dv dw, which is w squared times 3 sine 3w over cos squared 3w plus 2w sec 3w, and everything all divided by v squared, which means you'll get w squared sec 3w all squared. And again, you'll see I've not tried to simplify this in any way. There are some simplifications, but it isn't the purpose of this video to do that. Okay, next example. Find the derivative of h. Now in this case you're going to get worried because you'll see u of w is the product of three functions. Look, I've got a sine, I've got a cosine, and I've got a log. And you might be saying, golly, well, finding the derivative of even that numerator's a pain before I even go to the quotient formula. However, if you look at tables of known results for trigonometry, you'll see there's a possible double angle formula in the numerator. And so the key point of this example is to say always look for simplifications. Are there things you can do before you jump in to using the formula? So here I can recognize that this function can actually be simplified to the following form. So 6 sine 0.5w cos 0.5w is the same as 3 sine w using double angle formula. So now I've got a simple function, and you'll see what we've got to do next is say, okay, u is a product of two functions, v is a product of two functions. So I've got to use the product rule on each of these terms before I can move to the quotient rule. So here we go then. So find the derivatives of u and the derivatives of v using the product rule. So u is given by 3 sine w log 3w, and I'll write that as p times t, and there's the product rule. That should say u. So du dw equals p dt dw plus t dp dw. And I can work out p is 3 sine w, dp dw is 2 cos w. T is log 3w, dt dw is 1 over w. Similarly, for v, you'll see that v is e to the minus w tan 0.2w, which I've written as q times r, and so now dv dw is q dr dw plus r dq dw. And here you'll see q and dq dw defined there, e to the minus w and minus e to the minus w, and r and dr dw are defined there. So key point here is I'm trying to keep things neat and tidy. I've defined the numerator, I've defined the product rule, and then I've defined all the terms I'm going to use in the product rule. I've then defined the denominator, defined the corresponding product rule, and defined all the terms I'm going to use in that product rule. So I'm keeping it neat and tidy so things don't get mixed up. So now, let's put all those results together. So from the previous page, that was du dw, and that was dv dw. So now all I need to do is plug those in with the quotient rule. There's the quotient rule in order to find the answer. Now I may not have space to write this in full, but we'll illustrate what we've got. So we've got dh, dw, and what we're going to do is say, first of all, what's v? So it's e to the minus w tan 0.2 w, and that's going to be multiplied by du dw. So we've got 3 sine w all over w plus 2 cos w log 3w. So that's this term, v du dw. And then we're going to get minus, and we haven't got space for this obviously, we're going to get u dv dw. So I'm going to take u from here and dv dw from here. So I'm going to take those two terms, I'll just draw some arrows and plug them in here because I haven't got quite space to write it. But you can see the principle. I just take the numbers and plug them in. And then divided by v squared, so I'll get e to the minus w. Sorry, that's a line I didn't want there. So e to the minus w tan 0.2 w all squared. So a summary. This video has demonstrated the differentiation of commonplace functions using a lookup table in combination with the product and the quotient rules. And you'll see the most important points are: keep clear definitions of functions that you're using in the product and quotient rules, and clear definitions of their derivative before substituting them into the formula. Use a lookup table where you can for common results, and don't worry if the algebra gets messy. If you make sure the layout is clear, well organised, then you won't make mistakes.